These are notes about the factors that affect solubility and solubility curves. So um, if we think about, like, if we were trying to dissolve like sugar in our tea, we can make that sugar dissolve more quickly by grinding up the tea, like, I mean, not the tea, sorry, the sugar, so if no one uses them, but sugar cubes, if you were to have sugar cubes, you could crush them and then the sugar would dissolve more quickly. Stirring, we use our spoon and stir, and increasing temperature. So even if you're making tea that you want to have as being cold tea later, a lot of times you'll make it with sugar and make it while it's hot and then cool it so that you can get everything to dissolve more quickly. So that is the rate at which it dissolves. And now let's just talk about in general. Solubility is how much, like, we can quantify this, the number of grams of solute that can dissolve in a given amount of solvent. So this would be a number at a given temperature, and it's in water, and it's usually so many grams per 100 grams of water. So before we talk about solubility curves, just think about, like, what would affect the solubility of a gas in water. And a lot of you guys did, like the soda can fizzing for your phenomenon. So some of you were kind of getting into some of this. So pressure and temperature affect the solubility of a gas in a liquid. And we know that if we pour our LaCroix or whatever out on a warmer day, it's going to go flat more quickly because of the temperature. So the higher the temperature, the less dissolved gas you can have. And then pressure, we can't manipulate our pressure, but we do pressurize when we bottle things. We pressurize the bottle, and that's what allows more than normal carbonation. So this has a real world impact on with global warming. The pressure isn't changing with global warming, but temperature obviously is. So as temperature goes up, the oxygen level in a lake, stream, pond is going to go down. So you can see the requirements, the more the fish that people, I think, enjoy. I don't know, my family are all fisher people. They really enjoy catching these upper fish. Well, walleye's down pretty low. That's interesting. But salmon and trout, well, they're in a stream anyways, usually, so that they can get that more turned over oxygenated water. But even in Minnesota, like, some of the walleye lakes have been turning into northern pike lakes just because of that warming. So gases are less soluble as temperature goes up. And then if we think about just the pressure aspect, this would be our carbonated things. There is this law, Henry's law, that just says, and it kind of makes sense, that the solubility of the gas is directly proportional to the partial pressure of the gas on the surface of the liquid. So there's a pressure in a bottle of soda, LaCroix, whatever. There's carbon dioxide up here, and whatever that pressure is directly proportional to how much carbon dioxide gas is dissolved in the beverage. So what we were talking about, the factors that affect solubility of a gas in a liquid, and these other factors that affect, why is it that a certain number of grams of one ionic compound can dissolve versus, a different number of grams of another ionic compound in the same amount of water. And that's because of the nature of the solute and solvent. And what that means is, if you remember, I was talking about the IMFs. So in order for something to dissolve, you have to break the IMFs of the solute, break the IMFs of the solvent, usually water, then they form new IMFs. So sometimes that won't even happen if the solute's IMFs are really strong. So just how strong are they kind of is an indicator of how much will dissolve, if it does at all. And then temperature, as we increase temperature, you increase kinetic energy. Something will dissolve more quickly, but also more of it will dissolve if it's a solid in a liquid. less of it if it's a gas in a liquid. So if it's a solid in a liquid, as temperature goes up, more kinetic energy allows more movement and more ability to break those IMFs, so the solute, the solvent, so that they can then form their own new IMFs. So this is a solubility curve or graph, and what it is it's showing you several different solutes overlaid upon each other so that you don't have so many graphs. But when you read this, you only read one substance at a time. So you can see that most of these are going upward. As temperature increases, solubility goes up. So we would be suspicious that these would be solids they're in water, so we know they're in a liquid. This, NH3, we would probably guess is a gas. The solubility goes down as temperature goes up. So how do you read this? Let me show you. So if you're trying to figure out the solubility of something, like let's say it's potassium chloride, I'm only interested in that line. So I find it helpful to use like a highlighter because it can be a little overwhelming, all of these lines. And then we look at the temperature, 50 degrees, we go up, we intersect, and we come over. So it's about, and you and I can read this a little differently, and that's fine. So we could say 41 or 42 grams of potassium chloride are dissolved in 100 grams of water. So that's how you would express the solubility of something, is just reading the graph at that specific temperature. Just some terms in looking at the graph too. So let's say we're talking about, let's look at just any one of these substances. So let's look at the potassium dichromate here. And if I am on that line at any point, I know my line got messy, didn't it? If I'm on the line, that means I have a saturated solution, which means that it's holding the maximum amount of solute. If it's saturated, you don't necessarily know by looking at it unless you were to add a little bit more, and then it wouldn't dissolve at that specific temperature. If I'm below the line, like let's say it's 80 degrees and I have 40 grams of that potassium dichromate in 100 grams of water, then I would know it's unsaturated. And again, that could look the same as a saturated solution. The test to tell the difference would be to add a little bit more of that potassium dichromate, and then if it's unsaturated, it'll dissolve. And then supersaturated is if I were above the line. So let's say at 80 degrees, I have 80 grams of potassium dichromate dissolved. And that is not very common. But I do want to show you a couple examples of this. So here's one example.
So we have a supersaturated solution. There's more that can normally be dissolved in there at room temperature. It's very unstable. One way to get it to come out of its supersaturated state is just by vibrating it. Sometimes when I set it on the desk, that's enough for it to come out of its supersaturated state. Or the coolest way is by adding a seed crystal. So seed crystals of sodium acetate will allow those ions that are in their supersaturated state to recognize the crystal structure of these sodium acetate crystals, and they'll be attracted to it. And as that seed crystal gets bigger, more will be attracted to it. And as that gets bigger, more will be attracted to it, and exponentially gets larger until it goes back to its saturated state. Let me show you. Just a couple crystals. And if you zoom in, you might be able to see that sort of suspended in the middle of the solution there. And then those at the front of the room in just a moment will be able to see that begin to grow.
So all of that excess.
Can you all see that?
The excess solute that was dissolved in that supersaturated solution, all of a sudden becomes undissolved, and it just allows only that little top part of liquid now to be is saturated still. So it's not very common. Only certain substances will do this. And how do you make it? You have to make a saturated solution and then slowly, carefully cool it down. A more common example of this would be, let me show you. Actually, I'll show you here. Hand warmers. I don't know if you guys, I have these in the building and I would have used these today with you. What they are is they're reusable hand warmers, and there's a little disc in them, and as soon as you click it, then you get that same crystallization. They become essentially like a solid. There's a little bit of liquid saturated still in there. and then it happens to be exothermic, and that's why we do it. But it's a super saturated solution, and you can accidentally, like when I make these, I drop one or something and it will crystallize out. So they're kind of unstable, but they're really cool. So let's talk about, now it's just a few calculations and things with this solubility curve. So here's one example now of, there's several different types of calculations, and I think you'll find they're pretty easy, but I wanted to model it. So one thing, so here we have sodium nitrate. They want to know how many grams are going to dissolve if I only had 6 grams of water at 30 degrees. So when I read the graph, I'm only interested in the sodium nitrate, this line here. I would go 30 degrees up and over. So then I could see that, you know, maybe 96 grams of it would dissolve in 100 grams of water. So then I'm really just trying to figure out, well, what if I only had 6 grams of water? So then I can just cross multiply and I end up with about 5.8 grams of sodium nitrate would dissolve. So that's one type of problem. Another type is here where you're changing the temperature. So here we're using 100 grams of water, so we don't have to worry about changing the amount of water. But they're telling us that it's a saturated solution of potassium chloride, so we're using that line again down here, and at 70 degrees, and then we're going to lower it to 20, and how much is going to precipitate or, you know, become undissolved. So what I do is I break it into two for the two temps. I go 70 degrees up to the potassium chloride, and I come over. And again, you might read this, you know, a little different than me, just, you know, within a couple grams of what I say though. So 47 grams will dissolve in 100 grams of water at 70 degrees. And then at 20 degrees, if I go up to the potassium chloride and over, it's about 32 grams. So then I can just, you know, I know this much and this much. So the difference between them is how much will, is 15 grams. That's how much will precipitate or become undissolved.